So in today's lesson, 6.5, we're looking at the transformations of the sine function. Specifically today, we're going to be looking at both vertical and horizontal shifts. So I'm sort of jumping ahead by saying that, but the reason I'm saying it is because I really want you to build connections from what you've already done when we did the quadratic unit. So when you did the quadratic unit, remember you had your vertex form equation, which was y equals a x minus h squared plus k. And in this formula, remember the h right here, the thing that was inside the brackets, that meant your function was going to go left or go right. And then the thing on the backside, the k value, that determined if your function was going up or down. Well, look what we're going to get into. Notice how you have this number, this variable inside the brackets. So I want you to think of that as like this h value we see here. And then similarly, we have this d on the backside here. Think of that as this k value on the backside of your quadratic. And we'll see it. You'll see how they actually perform the same thing as what they did in quadratics, okay? Vertical shifts and horizontal shifts. So completing the table below, all right, you're evaluating our parent function. So let's compare what happens from when we add a plus 3 and a minus 3 on the backside to our parent function. So evaluating your parent function, again, you're just evaluating the function at these values here. So you're looking for f at 0 degrees. So that's sine at 0, which is going to be 0 by plugging it in. So then sine 90 is 1, sine 180 is 0, sine 270 is negative 1, and 360 is 0. So plot our parent function. So let's decide. We have to go up 3 and down 2. So if we call this 1, 2, 3, 4, and 5, we should be fine. 2, 3, 4, and 5. And let's make each one of these ticks on the horizontal 30 degrees. So then 30, 60, 90, 30, 60, 90. Oh, sorry, 180. 1, 2, 3, 270. 1, 2, 3, 360. Perfect. Okay, so graphing our parent, we are at the point 0, 0, 0, 0, 90 and 1 right here, 180 and 0 right there, 270 and negative 1, and 360 0. So your graph looks like this. Perfect. So there is your parent function. So now we're just going to visually look what happens when we introduce first this plus 3. So calculating all your points again, you're evaluating f at 0. So then you'd have sine of 0 degrees plus 3. So you evaluate this first. You type in your calculator sine 0. And you'll get 0 plus 3 is 3. Okay? So pretty much you're doing the same calculation, what you did before, but you're just adding 3. So sine of 90 is 1. Then add 3 to that is 4. Sine of 180 is 0. Add 3 to that, gives you 3. Negative 1 plus 3, 2. And then 0 plus 3 is 3. So let's plot those points. At 0 degrees, we are at 3. So that's way up here. At 90 degrees, we're at 4 up here. 180, it's 3. 270, it is 2. And 360, you're at 3. So if we connect our points, you can see that there is your purple graph. There is your new f of x function. And look, you are 1, 2, 3 units up. If you compare equivalent points, right? Like 1, 2, 3. You've moved 3 units up by just having this plus 3 on the backside here. Well, let's see what happens when we do it again, but this time for negative 2. So sine 0 degrees minus 2. Again, evaluate this first. So that's 0 minus 2, giving you negative 2. And then do that for each one. Minus 2 gives you minus 1. 0 minus 2 gives you minus 2. Negative 1 minus 2 gives you negative 3. 0 minus 2 gives you minus 2. plot those points. So at 0 degrees, you're at -2 down here. 90, it's -1. 180, you're -2. 270, -3. And 360, -2. So plot your points or connect your dots. And notice that if you even just look at the backside here, you are 2 units down from your parent function. And that's because you have this -2 on the backside. So if we complete the table based off our based off those 3 functions we've graphed here, well, the d value, remember it's sine x plus d. So what number do you see on the backside here on the first one? Nothing. 0. Okay, what about the other one? Well, we have 3 on the backside there and -2. Your amplitude, remember your amplitude is the distance from your max minus your min divided by 2. So if we do that for each one of these, so if we look at our parent function, your max is 1, your min is -1, divide that by 2, you get 2 over 2 or 1. Do that for the sine plus 3, so that's our purple graph. Its maximum, right here, its maximum is 4 minus its minimum, 2, all over 2, you get 2 over 2, and 1. So the amplitude stays the same. You have not changed the amplitude. Let's do it again for the -2 one. Your max right here is -1, and your min is -3. So -1 minus -3 over 2. That gives you up top 2 over 2 and 1. So notice that you have not changed the amplitude. The distance from your max and your min is identical. Let's look at the period. Well, our start of our function is right here at 0 degrees on every one of these graphs, and it finishes right here at 360. So your one cycle, your period from here to here is 360 degrees. So 360 degrees. 360 degrees. So the period has not changed. Your domain, okay, well, we're dealing with trig functions, so there isn't an angle that you can put. There is no restrictions. No restrictions on the domain, ever. So what that means is that every single one of these, your domain will be x can be any real number, okay? Always. Always. So this one will also have x belongs to real numbers. This one would also have the domain being x belongs to real numbers. There's no restriction. There is no value that you can put that you cannot take the sign of, okay? Just try it out for yourself. Put any number in there. You can always take the sign. The thing that changes, though, is your range, because remember, range deals with the y values. And in this case, what you are saying is like, what is your maximum and your minimum? So in general, your range formula is range for any trig function. Any trig function is x belongs to real numbers. Minimum, oh sorry, not x, y. Y is your minimum less than or equal to y less than or equal to max. So these two will change depending on what one we're looking at. And we've shown that. Like, look at our math back here where we had to use this formula, max and min. Notice how all the numbers are different. So what that means is that when we go to apply them into our range here, you could pretty much almost copy them right from that formula. Well, on your parent function, your minimum is -1. And then your maximum is 1. So that is your range. The one that was shifted up by 3, your max, I should start with your minimum first. Your minimum was 2, and then your maximum was 4. And then on the one that was shifted down to, your range, your minimum in this case was -3 y and -1. So really what changes, all right, when you have a d value is you're changing your range. You're changing the y's that your function is oscillating between. It has a vertical shift. So compare the graphs f of sine x to the graph f of d. Well, you have a vertical shift. You have a vertical shift up or down, up/down of d units. That's what happened. So when d is bigger than 0, meaning positive, then the graph of the sine x, in that case of the positive 3 here, well, it shifted up. And then when it was negative, your graph shifted down. And in general, your mapping rule is you're only dealing with the y values. Notice that your x's never change. So it was x, and then it was y's plus d, whatever they are. So that's your mapping rule. So in contrast, and again, let's go back to the analogy I put in the beginning. So notice how we're going to be dealing with these brackets now. Let's go back up to what I was saying at the beginning. In this one, remember what the h did, right? The thing that was inside the brackets. This was your horizontal shifts. So let's see what happens when we're just dealing with a different type of function. So in this case, now we're dealing with trig functions instead of quadratics. So fill in your parent function again. So 0 degrees, you're at 0. 90, you're 1. 180, 0. 270, -1. And 360, 0. Let's graph this. So make each one of the ticks 30 degrees. So that makes this 90. And then we'll do 1, 2, 3, 180. 1, 2, 3, 270. 1, 2, 3, 360. And yeah, I'll do one more. 1, 2, 3, 4, 50. Okay, and then do the same thing on the negative side. So you're going like -30, -60, -90. 1, 2, 3, -180. 1, 2, 3, -270. 1, 2, 3, -360. I got these tick markers right here. And then we'll do one more. 1, 2, 3, -450. Perfect. Okay, and remember this is 0, 0 right here. So let's plot our parent function. So we start here at the 0, 0, 0 degrees and 0. And then we go 90 and 1, so that would be right here. 180, 0, 270, -1, 360, 0. And let's connect our points. There's your parent. Okay, just like we did last time, let's plug in the new points and compare the graphs. So in this case right here, yes, we're putting them into the sine function, but still follow your function notation. You're inputting -90, okay? That's what this is saying right here. So that means you go sine, you plug in -90 for this x right here, plus 90, right? So you evaluate this first. I'm going to run out of room. I'll do it only for this first one, but you're essentially going sine then. What is -90 plus 90? Well, it ends up being 0. So you're actually taking the sine of 0, and that would give you 0. So this first one's 0. So in this one, I'll actually do one more, but this would be 0 degrees plus 90 degrees. Okay, so here, if you go 0 plus 90, you get 90. So you're taking the sine of 90 actually, and you get 1. And just follow that pattern for each one. So then if you plugged in 90 here, you would get sine 180 degrees after you did your addition, and you'd get 0. Here you'd do the sine, and you'd go 180 plus 90, so you end up with 270, and you get -1. And then here you do 270 plus 90, and you would get 360, so 0. So if we plot those points, and remember you're starting at -90 because that was the first point. So in this case, you're plotting -90 and 0. So -90 and 0 right here. Then you're plotting 0 degrees and 1, so right up here. 90 degrees and 0, right here. 180 and -1. And then 270 and 0. There we go. There is your new function. And notice how many spaces your new function has moved. Look at it. You've gone 1, 2, 3 spaces. And 3 spaces represents 90 degrees. So you've gone 90 degrees to the left. And look up here. Think back to your quadratic unit. You know, you see a positive in here and you think that you're going to go right, but you actually end up going left, right? So yes, it looks confusing because we're now dealing with degrees instead of just straight up numbers, but you are going left 90 degrees. Your function has shifted to the left. So if we do this math one more time, but with our new one being positive, and let's kind of come to a hypothesis before we even do it. That's negative 90, so we will expect this function to move to the right 90 degrees. But let's check. Let's do our math. So put in your first point, 90. So f at 90, we'll do a different color. F at 90 degrees, same thing we did before, is going to be sine 90. In this case, we're subtracting 90. So you're getting sine of 0 and 0. Do that again. F of 180 degrees. All right, you do your math there. You'd end up with the sine of 90, giving you 1. And do that for each one. So this would be the sine, I guess, end up being 180 after you take away 90 degrees. So then that would be 0. This would end up being the sine of 270. And you'd get negative 1. And this would end up being the sine of 360. And you would get 0. So we're graphing our function from 90 degrees to 450 and using those points we calculated. So if we start at 90 and we're at 0, so it's right here. 180, you're at 1, right there. 270 is 0, right there. 360, you're at negative 1. And 450, you're right here. So there is your new, sorry for the shaking, I'm going to do that again. There is your new function. And similarly, compared to the green one, notice how you've gone 1, 2, 3. You've gone 3 spaces, which is the same as 90 degrees on our scale. That's 90 degrees to the right. So yes, it is identical to what we did in quadratics. Let's fill in our chart here. Well, the value of c is what you see on the inside. So this one has 0, right? Well, this one, if you think of it, you see a positive. Remember, it's the opposite of what you see. So this one is actually minus 90 degrees. That's the value of c. It's minus 90. Well, here, if this is negative 90 on the inside, that means this had to be positive 90. It's the opposite. The amplitude, all right, same as before. It's max minus min all over 2. So if we look at our parent function, I mean, it's always the same. So this will always be 1. Subtract negative 1, max minus min, over 2. That's going to give you 1, right? So 2 over 2, 1. But notice how all of these have the same maximum, right? Like if you look, they all have the same max. Max is equal to 1 across all 3. And look, across all 3, you have the same min. The min is equal to 1. So you're essentially applying this formula 3 times. So each one of these will have the same amplitude. You have not changed the distance between your max and your min. All right, well, the period. Okay, so if we look at our parent function, our period is from here, 0, all the way over here to 360. Well, that's a period of 360 degrees. Well, let's look at our purple. We are going from negative 90, and then it takes us all the way to 270. Okay, so negative 90 to 270. Well, that is also a distance of 360 degrees. So 360 degrees. And then the blue one, if we go 90 and go all the way to where we end our pattern, right here, so that's 450. 450. And then this one is 90. Well, that also is a distance of 360. Same period again. These functions will always have the same period, okay? I'm just going to say that right now. It does not matter what transformation I'm going to give you, they will always have the same period. Okay. Lastly, domain and range. Well, your domain here, remember what I said, your domain never changes. It's still x belongs to real numbers. Yes, you are shifting your graph, but that's not what domain means. Domain is saying what values are restricted, what values can it not equal. So yes, you're moving it left and right, but it doesn't change anything, right? Think back to quadratics, right? Yes, you can have a quadratic here, and that was x belongs to real numbers. I can then put it all the way over here, but it's still x belongs to real numbers because it's fundamental to the type of function you're dealing with. So this domain is x belongs to real numbers. It's the same for each one of these. It never changes, okay? So that's a very easy 1-mark question on a test. What is the domain of a trig function? I can give you a transformation. You just have to know that it never changes. The range, remember, talks about your max and your min. But we showed that they all have the same max and they all have the same min. So all the ranges are going to be equal to each other. So, instead of me writing it 3 times, I'm just going to say the ranges are equal. Ranges are equal. And let's put it therefore, actually. Let's make it better. So ranges are equal because max / min are equal. So that means your range for all 3 of these will be the range of y belongs to real numbers between -1 and 1. There we go. So if we were to do a summary, the graph f of x, the graph compared to the graph f of x equals sine x, the graph f of x equals sine x represents a horizontal shift. Okay? That's all we have done. Left / right of c degrees, whatever it ends up being. So if c is greater than 0, okay, so again, positive, so that actually refers to this one right here, and that was our, I should have wrote that in blue so it's less confusing, 90. So that's our blue graph. Look what happened. It went to the right, okay? So when the c is bigger than 0, just like we did in the quadratic unit, you go to the right. And when the c is less than 0, and remember this means a c. This is not what you see in the bracket, right? So if you saw x minus 3, in this case, the c, yes, you think you see a negative here, but actually your c is positive 3, right? So it's the opposite. So really, this one right here, to answer this one, you would expect to see something like this, x plus 3. And that would be a c value being minus 3, c. So just make sure you don't make that mistake, okay? So if c is less than 0, the graph is shifted to the left, c degrees. Your mapping rule, well, this deals with left and right, so it's your x plus your c, right? It changes your x values, where you are left and right. Your y's remain unchanged. So let's look at our first example, first and last. Write the function f of x, the function f of x undergoes a horizontal translation of 25 degrees to the right and a vertical translation 3 up. Okay, so we're going to the right. So this horizontal translation to the right, that means you would expect inside the brackets to be a negative, right? Because you want to go to the right. And then 3 up, this is saying your d is 3. So if we write our new equation, f of x, well, it's going to be sine x, sine in brackets, x minus 25 degrees plus 3, because you're going up. State the amplitude, period, and equation of the axis of the new function. Well, your amplitude is your max and your min. So what would our max and our min be? What equation in the period and the equation of axis? So the amplitude is the max minus the min. over 2. And then the axis of symmetry, equation of the axis, all right? Well, that, and you know what, actually, you know, to answer this question, I'm going to jump ahead a lesson. I'm just going to say, instead of doing the math here, the amplitude is just whatever number you see in front of the sine right here. So you might be like, oh, well, I don't see a number there. Remember, there's always a 1 here. So the amplitude, our A, is 1. The equation of the axis is just the thing you see on the back here. It's your D value. So your D, and as we said in the previous lesson, your D is 3. So therefore, amplitude is 1, and axes, and you reported the axes as y equals 3, okay? Because when you look on a graph, it would be at 3, it would be a dotted line like this, and it'd have the function y equals 3. It's similar to like quadratics. Remember when you had the axis of symmetry and it was a vertical line, you would say x equals 3. You wouldn't say h equals 3, because I know it's like the variable h, but it's, you state the function, okay? You state what the equation of the line is. All right. And then the last part, state the period. The period is always 360 degrees. We proved it. We showed up here. It was always 360 degrees. It never changes. So your period, amplitude is 1, and your axis, y equals 3, and the period is 360 degrees. It does not change. State the domain. Domain is still the same. Does not change. X belongs to real numbers. Your range is your max and your min. So this, if we know our D, and this is why I wanted to jump ahead and show you this, okay? By just looking at an equation, getting your A and your D. Well, let's visualize. I kind of drew a graph right over here. You have a D at 3, so your axis is at 3, and your amplitude is 1. So that means your graph is going to go up 1 value from your axes. So 1 value off 3, that would correspond to a y value of 4. And then you'd be going 1 down, right? That's what the amplitude means. You'd be going 1 down below your axes, so your graph would look like this. Well, that's at a value of 2. So if your axis is at 3, well then your minimum is at 2, and your maximum is at 4, okay? So given an axis and an amplitude, you can find your max and your min so easily. All right, so there's our homework, and I'll see you next time.